Hi guys, I am going to discuss problem number 29 from chapter 23, the Gauss's law. I discussed this yesterday in the class. I'm going to discuss it again using the video. So please read the problem, pause it now and read the problem if you haven't already read that. So the part A is finding E at r equals to lowercase r equals to 2 times uppercase R2, and the values of R1 and R2 are given to us. So we are looking at a point outside the entire cylinder. So in order to find the E field, we need to use the Gauss's law. So if I write it down, this is what the Gauss's law says. E dotting to dA equals Q enclosed divided by epsilon naught. Now in order to use this Gaussian law, we have to choose an imaginary Gaussian surface. So the shape here is a cylinder. One is a conducting rod and the other one is a thin-walled coaxial cylindrical shell. So the best shape to fit this situation for a Gaussian surface, is a Gaussian cylinder. So outside, like 2 times R2 distance, I am going to draw the Gaussian surface, a cylinder, using this red dotted line. It's not a perfect one, but I think you guys understand what I mean here. So this is the Gaussian surface or the Gaussian cylinder. Now that I have marked the Gaussian surface, the cylinder, I am going to apply that and solve the problem. So here I have E dotted to dA, and E field is applied radially outward and it is parallel with the area vector. Therefore the dot product goes away, making the cosine angle between them a 0, right? If you want me to write down what I just said, this is what we have, and this side you have Q enclosed divided by epsilon naught. Cosine 0 is 1 and E is a constant, so you take it out, and then we have the loop integral dA, and this is the area of the Gaussian cylinder that we are looking at. And this side we have enclosed Q over epsilon naught. As we discussed yesterday, Q enclosed is the total Q enclosed by the chosen Gaussian surface, in this case a cylinder. So the Gaussian cylinder covers everything inside, which means Q1 and Q2 together can be found inside the Gaussian surface. So Q enclosed is the sum of Q1 and Q2. Now I did not necessarily look at the sign of the charges yet. I'm going to do that next. And this side I have E, and dA is the area of the Gaussian cylinder, and that is given by 2 pi r, actually the little r, let me erase that first. Okay, 2 pi r, and the length of the cylinder is L. On this side I have Q1, I'm going to use it as Q1, and Q2 is negative 2 Q1, and that is what is given in the problem. That makes it negative Q1 over epsilon naught. So your E equals negative Q1 over 2 pi r L and epsilon. If you want to substitute for Q1, that would be 3.4 times 10 to the negative 12 coulomb, and 2 pi r is 2 times r, big R2, and I'm going to substitute for that. R2 is 10 times R1, and R1 is 1.3. I don't want the dots to get confused as decimals, so 1.3, making it meters, millimeters into meters, dividing by 10 to the negative 3, and outside L 11 meters, and substitute for epsilon naught. And that is the answer for the electric field. And the electric field has a negative sign, and that tells us that the electric field is pointed inward. Inward direction. That's part A and part B. Okay, the second part of the problem, actually not the second, third and the fourth, C and D parts, you are supposed to find the electric field at a point R equals to 5 times R1 distance. So again, you are finding the electric field, therefore we are using the Gaussian law, E dotting to dA. At this point you should actually be able to write this without any problem. Q enclosed divided by epsilon, E dotted to dA equals to Q enclosed over epsilon naught. Now that we are looking at a point R equals to 5 times R1, now you know the relationship between R1 and R2, so definitely this R, the little r distance, is in between R1 and R2. So to find the electric field, we need an imaginary Gaussian surface. Again, we are choosing an imaginary Gaussian surface at a distance R1, at a distance R equals to 5 R1, and again we pick the shape of a cylinder. Cylinder has the radius R, and the length of the cylinder is L, as the two cylinder, the coaxial cable and the rod also have the same length L. Like last time, we take the dot product E dA cosine and again 0, because E field and the area vector, they are parallel to each other. And this case, enclosed Q is whatever the Q on the rod. So we have it as Q1. Outside it is given as Q2. So we are looking at the enclosed charge by the Gaussian sphere, Gaussian cylinder, and the enclosed charge by the Gaussian cylinder is Q1. So you have it as Q1, Q1 divided by epsilon naught. So I forgot the integral here. So electric field, a constant, cosine 0 is 1, and there you have the area integral dA, and Q1, as we know from before, is 3.4 times 10 to the negative 12 and divided by epsilon naught, the constant. And E dA, like last time, the area, the full area of the cylinder is 2 pi R and L. L is the length of the cylinder. 3.4 times 10 to the negative 12 divided by epsilon naught. So like last time, E equals 3.4 times 10 to the negative 12, 2 pi R L and epsilon naught. So this time R is different from last time, and also the enclosed charge has a positive value. And let me substitute for R. R is 5 times R1 and L and epsilon naught. L, epsilon naught, R1, you know the values of all those things, so I'm not going to waste too much time here substituting for those values, and I'm going to let you finish the problem. And here you have a positive sign, and that tells us the electric field is pointed outward. Pointed outward. Even if there is no sign, you should be able to tell the direction of the electric field, because we know when there is a positive charge, electric field is pointed outward. When there is a negative charge, the electric field is pointed inward. There. So we are done with C and D. So the last two parts, part E is finding the charge on the interior, and part F is finding the charge in the exterior surfaces of the shell. So I have marked them as Q in and Q exterior. So in order to make it simple, I drew the cylinder the side not the side view, actually the front view. So now we are looking at the front side of the shell and the rod, and I am drawing a Gaussian sphere inside the conducting shell. As we know, inside a conducting shell the electric field is 0 inside the shell, inside the conductor. E equals to 0. So in order for that to happen, enclosed Q also has to be a 0, because we know E dotting to dA equals to Q enclosed over epsilon naught by Gaussian law, and inside an electric conductor E field is 0, therefore the left hand side goes to 0 and the Q enclosed has to be 0 as well. So Q enclosed 0. Now if you look at this Gaussian cylinder, and in this case you can actually see it as a green circle, dotted circle inside the conducting shell, and if you look at that, the enclosed charge by the Gaussian surface in this case is Q1 plus Q interior. Now Q enclosed has to be 0, therefore you will have the internal charge Q internal equals to negative Q1, and Q1 is a positive 3.4, and with the negative sign you have the Q interior Q as 3.4 times 10 to the negative 12 coulomb. And in order to find the outside, I'm going to box this. In order to find the outside, you can actually do the same if you like. So at this point we are now looking at the external charge, and we know that the since the shell is known to have a total charge of Q2, which equals to negative 2 times Q1. This is actually given. This is given in the problem if you go back and read it. So negative 2 Q1, and if you look at the external, Q external should be the difference between Q2 and Q internal. That's pretty clear. So Q external equals negative 2 Q1, and Q internal turned out to be a negative Q1, so there you have that, and you end up with negative Q1 as the final answer for Q external. And that is the end of problem number 29. So please go over the video, and if you still have questions, please come and talk to me on Thursday.